Hi everyone. Have you ever wondered how we know what distant stars are actually made of, or just how neon lights work? So these are explained by emission and absorption spectra. This video will explain how atoms emit light and absorb light by exploring the world of light and energy levels. I hope you enjoy the video. Hi everybody, this is the final lesson in the quantum physics series of videos. This is on spectra. We're going to look at emission spectra, energy levels, and the absorption spectra. So what do we mean by spectra? So if we have a continuous spectrum, it looks like this. So you might observe this around the house even. If you have such things as DVDs and CDs, then the light reflected from them will give you all the colors of the rainbow. That's a continuous spectrum. So we get something called an emission spectrum if we shine light through a spectrometer. Now you don't need this fancy piece of kit. You can just have a single diffraction grating and you'll be able to see this yourself. But this is how to observe it more carefully. So we have something producing light. So it will be, for example, a helium discharge tube, so a single element in a gas tube that produces light of a specific wavelength or combination of wavelengths. And that shines through a tube called a collimator, through a diffraction grating, and then through a viewing column, which is a telescope. And if we look at that through this end here, through the eyepiece, then we would see something like this, an emission spectrum. So we've got particular coloured lines on a dark background. So lines of a very particular frequency or wavelength and a very particular spacing. So if we looked at helium, we might get something like this. If we looked at hydrogen or other elements, we would get a different set of lines. So this is particular for individual elements. So this is called an emission spectrum. This has been observed for a couple of hundred years, but this was only explained in the early 1900s as part of the quantum physics movement. We'll come on to absorption spectra and how they are produced later on in this video. Okay, so how do we explain these very particular lines? So this was first suggested by Niels Bohr in the early 1900s, and this is a fundamental aspect of quantum theory. So Bohr suggested that there are particular energy levels in an atom, and the electron can reside in each one of these energy levels, but only very particular, well-defined energy positions. And if an electron absorbs a photon of a very particular frequency, then it can jump up to a higher energy level, and it cannot stay there, so it will drop back down and emit a photon of a very particular wavelength or frequency. So if we look at an example, so we've got a hydrogen atom here, so we've got one proton in the nucleus and one electron, and normally that will be in its ground state, which is the lowest energy state down here. So let's say we have a photon of light comes in and that's absorbed by the electron, so that disappears, and the electron will jump up to the next energy level, which corresponds specifically to the energy of the photon. So the energy difference between these two, E1 minus E2, will correspond or must correspond exactly to the energy of the incoming photon. If it doesn't, then the energy of the photon will not be absorbed and this won't happen. Now the thing is about this electron here, it won't stay here. This is an unstable position, so it will drop back down almost immediately. When it does so, it will re-emit the same photon of energy. So it's absorbing energy and then re-emitting energy as photons. But the frequency of the photon, absorbed and emitted, must correspond exactly to the difference in these energy levels, E1 minus E2. So for example, if a different color photon, different frequency comes in, maybe that could be absorbed by this electron, so the photon disappears, and that might jump up to this gap here. So here we've got a difference in energy which corresponds to this particular frequency. Again, that electron cannot stay there, so it might drop back down to its ground state, and when it does, it will emit a photon of the same color as the photon that was absorbed. Right, let's have a think about the calculations involved in this process. So this is a little bit more complex. So let's imagine we've got hydrogen. So we have one proton in the nucleus, we've got one electron in its ground state, but there are multiple other energy levels where that electron could sit if we give it enough energy. So the ground state we refer to as n equals 1. The next energy level is n equals 2, 3, and 4. So we've got energy level 1, 2, 3, 4. There are other ones that we could consider, but normally we just consider the first few. Each of these energy levels is associated with a particular energy, and this will be a tiny amount of joules, so always watch out for this. So we've got 21.8, 10 to the minus 19, 5.45, 10 to the minus 19. So we always need to look at this power of 10 here, because it'll be a very, very small amount. The negative signs, if we want to, we could just ignore them, because we're only interested in the difference between the two. So if you don't like the negative signs, we can just disregard them. But they are there for a purpose, because if you imagine removing the electron totally from the atom, so it's as far away from the nucleus as possible, then it will have zero energy, zero potential energy. So it's going to have a lower energy as it drops further down towards the nucleus, because we have to put energy in to remove the electron to overcome the electrostatic force of attraction between the proton and the electron. So the negative signs are significant, they are important, but if you prefer, you can just ignore them and the calculations will come out the same way. So if we're doing calculations, we need to consider E1 minus E2. Now, it doesn't matter which is E1 and E2, it's just the difference between two particular energy levels. And that will correspond precisely to HF, which is the energy of the incoming photon, or indeed the energy of the photon emitted. Right, let's have a look at a worked example. If you want to pause the video and try these questions, that's a good idea. Question 1 says, how many possible absorption transitions are there? Okay, so we've got our electron in its ground state. That could absorb a photon and jump to position 2. It might absorb a different coloured photon and jump to position 3, or a third photon and jump to position 4. So that's 3 possible absorption transitions. But before it drops down from position 2, it might absorb another photon and jump from either 2 to 3 or 2 to 4. So that's 2 more. And if it's position 3, then it might absorb another photon and jump up to position 4. So that's 6 in total. All of these are absorption transitions. A photon is absorbed. So when the electron drops back down again, then there are also 6 possible transitions, but these will be 6 emission transitions. So we need to make the distinction between absorption transitions and emission transitions. Who says, what is the minimum energy needed to excite an electron? So we always assume that the electron starts in its lowest state, n equals 1, referred to as the ground state. So the minimum energy to excite it, that means to give it more energy, would be to make it jump between 1 and 2. So we need to look at the difference between these two values. As we said before, if you don't like the negative sign, just ignore those, but we do need to take into account the 10 to the minus 19. So it's going to be the difference between those two values, 21.8, take away 5.45, all 10 to the minus 19, and we get this value here. So that is the difference in energy. So we want a photon with that particular energy in order for this to happen, either to be the photon to be absorbed or the photon to be emitted. So question 3 follows on from that. What is the wavelength of that light? So we need to use this expression here, which we've seen before. So E equals hc over lambda, make lambda the subject, lambda equals hc over E. So we've got Planck's constant, c is the speed of light, divided by your previous value, will give you 122 10 to the minus 9, which is nanometers. So this is slightly shorter wavelength than visible violet light, so this is going to be invisible UV light. So the final question, part 4, is a little bit more like an exam question. So we're told we have a photon energy of 2.56 eV. So the first thing we need to do is to convert that into our joules, so we multiply by 1.6 10 to the minus 19. And then we need to look at the options here, and by a process of trial and error, work out which of these differences, so is it 1 to 2 or 1 to 3 or 1 to 4, will give us a value of 4 10 to the minus 19. So this can be a little bit intimidating, a little bit tedious, because we're not sure where to start. So you might just need to try a few differences to find which one is correct. But if we look at n equals 4, that's 1.36, and n equals 2, that's 5.45. The difference between those two is 4.09, which is pretty much what we have here. So the answer is, it's the difference between 4 and 2 And because it's an emission spectrum, then we need to say that it's fallen from 4 to 2. And very often in the exam, you need to draw an arrow to indicate the direction. So just identifying that it's 4 and 2 will not be sufficient. We need to say that it's falling from 4 to 2, which will correspond to this particular energy difference, and that will corresponding to the particular photon emitted in this case. Right, the final thing we need to consider is something called an absorption spectrum, or absorption spectra. So the best way to consider this is if you imagine that we're viewing through a telescope on Earth the light from a distant star. So if the light comes from the star and it doesn't pass through anything on the way, then we're going to get, hopefully, a continuous spectrum. Now, that's probably unlikely because there will be gases in the atmosphere of the star and it's going to pass through nebula on the way. But if there was nothing in the way and we just had white light through a diffraction grating, we would get all the colours of the rainbow, a continuous spectrum. Right, what about if that light passes through a cloud of gas, let's say hydrogen gas? Now that could be the atmosphere around the star, or it could be a nebula between Earth and this particular star we're looking at. Well, in that case, we're going to get an absorption spectrum. So we need to think, well, why do we get an absorption spectrum? Why would we get the continuous spectrum with all these lines missing, and these lines correspond to the difference in energy levels that we talked about previously? So we need to think about what's happening in the gas cloud. So the gas cloud, let's say it's a hydrogen gas. So we're going to get particular photons coming in, which will be absorbed up to a higher energy level, and then they're going to drop back down and emit photons of a particular frequency, a wavelength. So we should expect, well, why are we not getting an emission spectrum? Now, the thing is here is that the electrons are absorbed and re-emitted, but these will be re-emitted in all directions, not just the one direction that we're looking at the light coming from. So rather than being absorbed and re-emitted and filling in all of these lines, because these lines correspond to wavelengths which are emitted in all directions, and the vast majority of those photons will not be coming back towards us, then effectively we can no longer see them. So in summary, an absorption spectrum is when a gas is backlit, so the energy which has been absorbed and re-emitted, because it's in all directions, we are then missing those particular wavelengths on the backdrop of the continuous spectrum. Right, so a couple of exam questions for you to have a go at. I recommend you pause the video, get a pen and paper and a calculator, try these on your own, and then you can check your answers when you've finished. Okay, question 1. So this is a fairly typical exam question, relatively straightforward. So part A says, what energy must an electron absorb to move from the ground state to the second energy level? So it's told us specifically what the two energy levels are, and this is in joules rather than EV, so it's just the difference between these two. As mentioned before, if you'd rather ignore the negative sign to make life easier, that's absolutely fine. It's just the difference between the two, but make sure you include the 10 to the minus 19. That's very important. B, straightforward. We know E equals hc over lambda, to make lambda the subject, hc over E, and we've got Planck multiplied by speed of light divided by your previous value, and you're going to get the wavelength as shown. So an exam tip here would be make sure you show all your working out, because in a multi-stage calculation like this, if for some reason you made a mistake in part A, but you didn't show all your working out in part B, you would get 0 marks. If you show your working out, you get error carried forward, and you should get full marks even if your answer is incorrect. C, if the electron falls from the 4th energy level, how many different frequencies could be emitted? Well, we talked about this before. So we could go from 4 to 3, 4 to 2, 4 to 1, that's 3. If we're at 3, we could drop down to 2 and then down to 1, or we could go all the way down to 1. So there are 6 possible frequencies, 6 possible wavelengths. So that corresponds to 6 lines on our spectra, whether it's emission or absorption. Right, question 2, another fairly typical exam question. So it tells us we've got 3 energy levels here, and it tells us what's going on. The electron jumps from 1 to 2 and then back down to 1. So absorbed and then re-emitted. Calculate the frequency. Okay, so we need to look at the difference between these two energy values. We can ignore the negative if you prefer. So the difference is 10.19 eV. We need to convert that into joules, so multiply by 1.6 10 to the minus 19, and that is our value in joules. And then we're trying to find the frequency, so we know E equals hf, make f the subject, so it's going to be your previous answer divided by the Planck constant, and we get our frequency as shown, 2.46 10 to the 15. Part B, show that the original photon cannot excite the electron in the ground state to the third energy level. Right, so this is the idea of particular transitions correspond to particular energies of photons. So if we work out the energy difference between 1 and 3, so 13.6 take away 1.51, 12.09. If we compare that to the previous value, which is 10.19, then it's obviously a different value. So all we need to say is the energy difference is a different value, therefore the first photon will not correspond to this transition between 1 and 3. Right, C, when they're excited to the third energy level, we get multiple frequencies. Okay, so once again, this is similar to what we were saying before. So if it's in position 3, it could drop to 2, or it could drop to 1, or it could drop from 2 to 1. So there are 3 possible transitions. They're very similar to what we said previously. Right, well done everyone. You've got to the end of this video. So there's a lot of very difficult ideas here. We looked at how an emission spectrum is produced and the calculation of energies and frequencies. And we also looked at an absorption spectra as well. So well done. That's the final video in the quantum physics series. If you're looking for more videos, I'd recommend looking at the waves playlists or the electricity playlists, and there will be other videos coming soon. So check those out. See you next time.